Alright, so let's say that you're trying to slide a heavy sofa over your carpeted floor. Your sofa has a mass of 127 kilograms, and the coefficient of static friction between the feet of the sofa and the carpet is 0.3. What is the minimum applied force that you would need to push on the sofa with to cause it to start moving? Now, it asks for the minimum applied force. In this case, what it's really saying is, can you solve for the maximum force of static friction, right? Any force over the maximum force of static friction would be enough to cause the sofa to start moving. So in this problem, we'll be solving for the maximum force of static friction possible between the sofa and the carpet. To begin solving this problem and all problems in this unit, I'll begin by drawing an interaction diagram. I'll begin by listing all of the objects in my system, and then labeling all of my interactions. Notice we have two interactions between the floor and the sofa. The first interaction is the normal force interaction, and the second interaction is our static frictional force interaction. So when I look at the sofa, I see I have four interactions between the sofa and other objects. The next thing I'll do is draw a force diagram for the sofa. I've gone ahead and drawn my force diagram for the sofa and labeled my four interactions. The normal force provided by the floor on the sofa is pointing upwards. The gravitational force provided by the earth on the sofa is pointing downwards. The applied force provided by the person on the sofa, and the force of static friction between the floor and the sofa is pointing to the left. In this case, I've assumed the person is pushing to the right. You could assume they were pushing to the left, but in either case, friction would oppose the applied force. Now, I've also gone ahead and drawn in, just as a shorthand, oftentimes when we're solving simple problems like this, we'll call the one normal force we have Fn, and the gravitational force or the weight of the sofa Fg. So I just wanted you to see this nomenclature. If you see Fn and Fg, that's talking about the normal force provided by the floor on the sofa, and Fg would be the Earth's force on the sofa, otherwise known as the weight, right? Then the applied force is just a contact force, but sometimes we'll call it applied to be clear that it's the applied force by some person or some agent. And then Fs indicates the static frictional force between the floor and the sofa. But you'll notice I've also included the agent-object notation, as always, to be very explicit about the source of that force and the object of that force, in this case, the sofa. Okay, now that I've drawn my interaction diagram and my force diagram, I will go ahead and write out the sum of forces in the horizontal and vertical direction, looking out for my static frictional force. That's what I'm trying to solve in this problem. So in this case, if I call the up and right directions positive, then the sum of forces in the y direction would be the normal force Fn minus the gravitational force on the sofa Fg. And because I know that this is equal to m times ay, where m is the mass of the sofa, and I know that the sofa is not accelerating vertically, I can say this is equal to 0, right? This is from Newton's second law. Now, I can also do this for the sum of forces in the x direction. Since right is positive, that would be the applied force minus the force of static friction. Again, this sum of forces, or net force, is equal to the mass of the sofa times the acceleration of the sofa in the x direction by Newton's second law. And I'm essentially looking for the moment when m times ax is really just greater than 0, right? I would normally say this is equal to 0, but I'm looking for the minimum force required to just begin the sofa to start moving, so to give it really any acceleration. So I'll say that it's greater than 0. Right? You don't need to worry about that too much. Really, all that's going to do is tell us that the applied force is going to be greater than the static frictional force at its highest value. And we already knew that from reading the problem. So we're not really going to use the x equation anymore to solve this problem. But let's write out the expression since we're using the de Gepsa problem solving process here. We've already drawn our diagram. We have our given information right there in the problem. We can go ahead and circle that. The coefficient of static friction is 0.3. That's our mu sub s. And this is our mass, the mass of the sofa. So we've identified that already. Good. And then we've identified our unknown. Again, we said we were looking for this maximum static frictional force. So our equations are as follows. We have Newton's second law, but we have one more equation, right? We're looking for the maximum static frictional force. I know that Fs max is equal to the coefficient of static friction times the normal force, right? That was from our previous video. So what I'm essentially saying is if I want the static frictional force at its largest value, I need the coefficient of static friction and the normal force. Do I know the coefficient of static friction? I do. This is 0.3. So really, the problem becomes solve for Fn. Okay. Now, how can I solve for the normal force? Well, I see here in my sum of the forces in the y direction, I have the normal force right there. So I'm going to use this equation to solve for Fn. So if I were to do the P into GEPSA and plan, I'm going to say, let's call this equation 1. Let's say use 1 to get Fn, and then I'm going to plug it in here to equation 2. So plug Fn into equation 2. All right, let's do it. So if I write out down here, if Fn minus Fg is 0, that means that the normal force must be equal to the weight, essentially, of the sofa, right? Fg is like the weight of the sofa, which we know is m sofa times g, right? M times g. I'll put the multiplication sign there. Okay. And that would be equal to 127 kilograms, again, times our constant here, a positive 9.8 meters per second squared, which is equal to 1,244.6 newtons. All right, and we've seen this for several examples now. When we have an object at rest and there are no other forces acting in the vertical direction, the normal force is equal to the gravitational force only in this scenario, though, right? Not always. So I can go ahead and take this value now and plug this in up here, which will give me Fs max is equal to 0.3 times this normal force in newtons, which will give me a static frictional force of 373.4 newtons. And so what that means is that our minimum applied force, right, the applied force must be anything, even 0.1 newtons, greater than 373.4 newtons, right? That's from my second law equation right here. I got that earlier. Okay, so in order to solve, again, this problem, we made an interaction diagram, we drew a force diagram, we wrote out the sum of forces in the x and y direction, and set that equal to the mass times acceleration through Newton's second law. We wrote out our expression for the static frictional force from earlier. We knew that was equal to the coefficient times the normal force, and we used the forces in the y direction to get our normal force, and we plugged in our values. So let's take a look at an example now for kinetic friction.